So the standard basis for, let's say, the vector space R2, two-dimensional space, consists of the vectors 1, 0, and 0, 1. And the multiples of those vectors kind of trace out these vertical and horizontal lines on our graph paper, right? They're the lines that are spaced apart by ones, right? Here's 1 times v, 2 times v, 3 times v, 1 times w, 2 times w, 3 times w. And the coordinates of any point in that space are just determined by how many v's and how many w's I need to add together to give me my vector. But it's not the only basis that we can choose for a vector space. I could take a different set of two vectors that is still a spanning set for the xy plane, and it's also still linearly independent, and I'll get a different basis. So I don't know, what if I chose the vector -1, 1 and the vector 2, 1? What I'm getting is I'm getting a new coordinate system. It's like a new type of graph paper laid down on top of my old one. And now every point in my coordinate system has both a expression in terms of the original standard basis and also an expression in terms of coordinates in my new graph paper, in my new basis. So for example, the point which in the ordinary coordinates is called 1, 2, right, in the standard basis. In my new basis of this v and this w, it's called 1, 1, because to get there, I just need to go one unit in my new v direction and add that to one copy of my new w direction. So in my new graph paper, it sits at the coordinates 1, 1, even though in my original graph paper, it had the coordinates 1, 2. And so as you can see, any way in which I can sort of choose a parallelogram grid on the xy plane is going to give me a new kind of basis for the xy plane. And as we go through the semester, and especially as we get toward the end of the course where we start to really focus on the geometric properties of linear transformations, it's going to be a really valuable thing for us to be able to choose a convenient basis for a vector space to work in, because that's going to be what allows us to best understand what a linear transformation is doing by looking at a basis in which it is acting as simply as possible. So this is the first sort of taste of what it means to choose a basis, because to choose a basis is to confer a coordinate system on a vector space, to describe how to locate any point inside of my vector space as some multiple of one of my vectors plus some multiple of another. And that expression not only exists for every point in my vector space because a basis is a spanning set, it's also uniquely determined because a basis is a linearly independent set, that there's only one way to describe any given point in a vector space as a linear combination of the elements of a basis for that space. So, to get us warmed up, excuse me, the activity is as follows. I have here a collection of 5 different collections of vectors inside of 4-dimensional space. And to streamline things, I think I would like for each group, first of all, to immediately rule out some examples. Let me zoom out because we can't quite see everything here. Your first step when you do activity 261 should be to immediately rule out which of these do we definitely not think are going to be basis for 4-dimensional space, based on what we know about 4-dimensional space. And then for those that remain, see if you can set up a linear system of equations, find a reduced row echelon form of some matrix that can tell you, first of all, whether or not this set of vectors is linearly independent, and second of all, whether or not this set of vectors is a spanning set for 4-dimensional space. So let's take 15 minutes on activity 261 with your teams. Again, these are new teams relative to what we're used to working with today. All right, welcome back. Nice work on this activity where we had to figure out which of these options of vectors in 4-dimensional space were a basis for R4. And so immediately you were able to throw out a couple of options that couldn't be basis because one of these, even before you do any calculation, can definitely not be linearly independent set. And the reason that it can't be a linearly independent set is that it has too many vectors that belong to it. Right? That's the set C. The set C can't be linearly independent because they're 4-dimensional vectors and we have 5 of them. And so when we put those into a matrix and find the reduced row echelon form, we're going to get, I'm going to put the other team's work up here in the thing right here. When we find that reduced row echelon form, we're definitely going to get a matrix that has more columns than it has rows. And since it has more columns than it has rows, even before we did the calculation, we could have known that it couldn't possibly have a pivot in every column, which is what's necessary to indicate linear independence. Remember, that was the last thing that we learned in our last class, was that for a linearly independent set of vectors, when you put them in the columns of a matrix and find the reduced row echelon form, every single column is going to have a pivot because there are no free variables in the solution of the homogeneous equation involving those vectors, if I have a linearly independent set. And so even before we do any calculation, we know that a set of 5 vectors that have 4 components in them cannot be a linearly independent set. So there's no way that can be a basis. Similarly, there's a set of vectors here that cannot possibly be a spanning set for R4, and that's the set E right here. Because E has 3 vectors in it, but the vectors have 4 components, there is no possible way for us to make a system of equations that can't possibly be inconsistent, because we're guaranteed to get at least one row of all zeros down at the bottom of our RREF. So we have to have that row of zeros at the bottom of the RREF because we have too many rows relative to the number of columns that we have. And so this set cannot be a spanning set for R4. So neither of those can be a basis, but you can still do the work and figure out which ones are linearly independent and which ones are, in fact, spanning sets. And it all depends on how many pivots are present in the reduced row echelon form. If every column has a pivot, then we have a linearly independent set. If every row has a pivot, then we have a spanning set for R4. And if both of those things happen simultaneously, that's when we have a basis for R4. And so in doing these calculations, you figured out that A is actually the standard basis for R4. So that one probably only took a little bit of inspection. You don't have to do any RREF because by the time you put those columns in a matrix, that matrix is already the RREF. And it has 4 pivots in it, 1 for every row and 1 for every column. 1 for every row means that it's a spanning set for R4. 1 for every column means that it's a linearly independent set. Therefore, it's a basis. And the same thing was true for the set D. That even though we couldn't have known right off the bat whether the set D was a basis for R4, by the time you put it into a matrix and find its reduced row echelon form is the same as the reduced row echelon form for A was. So actually, this matrix and the matrix of the A's are equivalent to one another in a row operations sense. And so D forms the basis for the same reason that A does. It's a spanning set because there's a pivot in every row. It's linearly independent because there's a pivot in every column. And so the only really kind of interesting one is B, that it has the right number of vectors in it to potentially be a basis for R4. But when you put the vectors into the columns of a matrix and row reduce, the reduced row echelon form that you get, and I want to see what this team wrote about it, it is a spanning set. Well, let's see. So what is it lacking? It has 3 pivots in total. And so it doesn't have a pivot in every column. And because it doesn't have a pivot in every column, there's a column, namely the 3rd column here, which corresponds to a free variable in the homogeneous equation for these vectors. So that means that this set of vectors is not linearly independent because it's missing a pivot column. Right? There's a free variable involved. But also, I'm going to take the liberty here of moving this statement from B down to C, or from the first piece down to the second piece. We don't have a spanning set for R4. And the reason we don't have a spanning set is that we lack a pivot in a row. Right? This last row of the reduced row echelon form for B is all zeros, which means that there exists some vector out there in 4-dimensional space such that if I made it the right-hand side of an augmented matrix against this left-hand side, that we would get an inconsistency. We would get a contradiction in that last row because we'd get zeros on the left-hand side of the bar, but we'd get some other number, probably 1, on the right-hand side of the bar. And that contradiction shows me that it's possible to get an inconsistent system, a vector in 4-dimensional space, which is not a linear combination of the 4 vectors in my set B. Therefore, B cannot span all of 4-dimensional space. So it's not linearly independent, and it's not a spanning set. Right? Even though it had the right number of vectors in it to be a basis, it ends up failing both of the criteria that we would need it to satisfy.